This week, we've got Jude, Reed, Pavi, and Aaron joining us. Any questions, raise your hand. Happy to welcome you in. All right, take it away, guys.
Awesome. Thanks, Shannon. So today we're talking about SIP-006, which is about clarity execution cost assessment. So yeah, it details how costs are measured and how costs are assessed for the execution of clarity code. Maybe, I guess to start off, I'd be curious to hear from Aaron about when you guys were initially thinking about costs and clarity, I assume you guys were thinking about how things were done in the Ethereum world, and I'm curious, what were kind of the design constraints in your head, and how did you want to perhaps try to improve on what was being done in the Ethereum world? Can anyone else hear Aaron? It looks like he's
No, I
muted,
can't.
but
Yep.
I'm having trouble hearing him.
Yeah, sorry, Aaron. Looks like your sound is not working.
It was just me for a sec, but maybe Jude, would you want to take this one while Aaron figures out his mic?
Sure. You want to repeat the question?
Yeah. I was just curious, when you guys were initially thinking about how cost assessment and cost functions should work in Clarity, what were the criteria, I guess, for designing the system, and how did you how are you thinking about it versus something like Ethereum, and were there ways in which you wanted to improve on the way that Ethereum was doing it?
Sure. Probably the biggest pain point that we thought that we could solve that we'd seen in Ethereum and other Turing-complete blockchains is this notion of removing the possibility of this notion of what's called an out-of-gas error. So in blockchains whose runtime systems are at least nominally Turing-complete, where the system cannot determine in advance whether or not a particular smart contract code snippet will halt or reach a certain halting state within a certain amount of steps or memory resources used. The only recourse you have is to just have the VM just count up the number of steps or the amount of resources the transaction uses as it's running. And if a certain threshold is reached, like the gas limit in Ethereum's case, you just take the user's transaction fee and you say, too bad, you ran out of time, your code's not going to run to completion, you're out the transaction fee. That's a really bad user experience when you think about it. In the case of a congested blockchain like Ethereum, you might end up spending on the order of $100 in gas only for your transaction to just get mined but not materialize. Bitcoin does not have this problem by comparison, nor do any systems derived from Bitcoin, in part because the the programming language and the scripting system they have is decidable, but more specifically, it's decidable in such a way that you can tell just by looking at the transaction how much compute resources it could conceivably take, and thus thereby allowing miners to simply not mine your transaction if they know you're not paying enough for it. So as a contrast to Ethereum, you have this other alternative runtime system where your transaction either gets mined and runs, or it does not get mined but does not run, but you're only out the transaction fee if it runs. So what the design of Clarity is meant to achieve in this particular aspect is to bring that property of Bitcoin. So transaction either runs and you're out your fee, or it does not run and you're not out your fee, but no out-of-gas errors. Bring that property to a much more expressive scripting language, but without having to introduce the notion of Turing completeness, which would make all such analysis impossible, or at least not feasible in a general sense.
So thanks, Jude.
Mm-hmm.
Do you want to go ahead with follow-up question?
Sure, unless Aaron is back online with his mic.
Oh yeah, I'm not sure if Aaron's back. I was going to ask, Pavi, do you want to follow that up?
Sure. What's the question?
Oh no, so I was asking if Pavi had a follow-up question, but I'm not really sure if her mic is. I can't seem to hear her if she's trying to talk. Anyway, let's keep going.
Sorry.
Oh, no worries. Go for it, Pavi.
Yeah. We just asked the next question. It's fine.
Yeah, so I was just going to ask then. So, like, how do we actually break down execution cost? I know, in Clarity language, we have like 5 different categories of cost. Could you maybe detail like what those are, Jude?
Yeah, sure. So, just like any computing facility, the Clarity runtime has certain different types of computing resources at your disposal. In a normal computer, you have things like RAM or CPU time, persistent storage space, network bandwidth, stuff like that. There's an analogous set of resources in the Clarity runtime, but they're very specific to a programming environment that you would expect from a smart contract language runtime. And there are 5 such resources in our case. Those resources are just a generic runtime metric. So that's like CPU and RAM usage. Each act of running a particular type of computation, like creating a variable or adding 2 numbers, comparing strings, stuff like that. That all consumes a runtime, a number of runtime units, of which a block, or more specifically an epoch, so the block plus the microblocks it confirms, all consume. So I believe the runtime budget on mainnet is like 500 billion or something like that. I'd have to go double check. It's big. And anyway, like there's a set of Clarity functions defined in the boot code that tell you how much runtime every Clarity built-in will take. And there's even a way to change them through a token and miner vote, but more on that later. But the point is, there's this notion of a runtime metric that captures like CPU and RAM use. So just transient state and time spent doing computation. There's also the remaining 4 metrics are concerned with persistent storage. There's this notion of what's called a read count and a read bandwidth. So in the context of blockchain, one of the things you have to consider when reading persistent state, like state from your current smart contract, but that was written in a prior block, there's 2 aspects to this. There's this notion of reading the actual data. So you might read, 8 bytes, 20 bytes, 150 bytes, whatever. So there's that notion of bandwidth. But there's also this notion of looking up that prior state in the past. Per SIP-004, we have this forkable hash table, you can think of it, called a MARF, which allows us to efficiently represent all of the data, all the persisted data in a blockchain, but in such a way that given a chain tip, you can look at any prior stored key value pair within that fork. But the act of looking up that data, traversing the MARF to find the key value pair, is a separate compute resource you can consume from just the data being read, because it turns out traversing this index is somewhat costly because you have to do a lot of disk seeks. So you can kind of think of the act of read count as like number of disk seeks you're allowed in the process of walking the MARF data structure back to a key value pair you want to read. Once you have seeked to the right location on disk, then the read bandwidth just captures the notion of streaming that data off of persistent storage and into RAM. So you can start computing on it. The remaining 2 compute limits that we have in Clarity are the analogs for write. So the notion of a write count and write bandwidth. Write count being the act of making a new index node or an index path in the MARF data structure, and then the act of actually persisting and storing that data once you have created the path to it within the MARF. So those 5 resources we have: the runtime, which is CPU and RAM use, and read bandwidth and read count, which respectively are streaming data from disk and looking up data on disk, and then write bandwidth and write count, respectively serializing data to disk and making it indexable for a future read.
Thanks, Jude. So I kind of just want to like try and summarize, I guess, a little bit of like what the purpose of this document is, because I feel like the first time I was thinking about this, it was a little bit confusing to me. So like we're trying to be able to have like some sort of metric or execution cost for an arbitrary block clarity code, right? And the purpose being like we need to like we don't want to put too many things in too many transactions or too many whatever in a block because we might run out of resources. Is that kind of like a correct way to be thinking about like what the goal is with computing runtime costs here?
Yeah, absolutely. So if you make a block that's too big, it's invalid. So if you're a miner that makes a block such that when you run the transactions to completion, if the total budget on any of these 5 dimensions is exceeded, block processing stops, the block is declared invalid, and as a miner, you've lost your Coinbase. So you just wasted Bitcoin for nothing.
Right. You had a question?
Yeah, I did have a question. Yeah, Jude, I was kind of curious how we arrived at our limit for the runtime, which is like 500 billion.
To be honest, like we probably should have done a better job at it. This is something that is very difficult in general to measure because you really just have to benchmark all of the implementations of your Clarity built-ins in order to figure out like how relatively expensive they are to one another. It's really difficult to get this right, not only because you want to make sure to choose a runtime consumption for a particular method that reflects the not only the asymptotic behavior of that built-in, but also the actual like best possible runtime that can be done on contemporary hardware in the implementation. That latter one is particularly difficult to get right because you're always going to think of a better implementation after you ship it. And in the realm of blockchains, you don't really have a second chance to change consensus critical code short of doing a hard fork. We de-risk this in the design of Clarity by making it so that you can vote on what should be the runtime cost for any Clarity function, including a built-in, like after the fact. So like consider, for example, the notion of verifying a signature, a SEC-P256K1 signature. Suppose 5 years from now, let's say, Intel and AMD both have hardware instructions now for doing this. And suppose that they are like an order of magnitude faster, let's say, than the software implementation we're using right now. It would be really great if the runtime cost assessed to these operations in Clarity could accurately reflect this now. Like, why should verifying a signature be 10 times as expensive on the transaction sender as it really could be? So we implemented this notion of cost voting such that the people who hold the stacks and the miners in the system have the ability to say, oh, well, now we can just declare that the runtime for this particular method is smaller or even larger. Like, I don't really see it going the other direction because computers tend to get better over time, but we have this ability to let the market decide how much these particular methods should cost within the block budget in a way that reflects the will of all the stakeholders affected. So to answer your question, like, it's actually basically impossible to do a good job at picking these initial constants because you're basically because the act of trying to do so is the act of declaring that you know that you have the best possible implementation forever. So we did not do that. We just declared some reasonable boundaries, some reasonable runtime costs on all the Clarity methods, then made it so that you can change them later without having to upgrade the chain in a backwards incompatible way. By way of comparison, Ethereum has to hard fork every time they do this. And if you look at the release notes for all of Ethereum's hard forks, there's always a few things about how they're making certain opcodes cost more or less gas.
Cool. Thanks for the explanation. Yeah, so moving on to the next question. I guess one thing that kind of came up in the SIP was that static and dynamic cost assessment is like necessarily like different. Could you explain that difference?
Yeah, sure. So the two properties that we have that Ethereum does not have here, like this notion that your transaction gets mined or it does not get mined, but there's no out of gas error. And also this notion that the block limit, the block compute size is fixed by the protocol. I guess Ethereum does have that with their gas limit, but their gas limit can be adjusted by miners dynamically. But in our case, it is fixed. Like you try to make a block that's too big, it gets orphaned. It doesn't even get processed and you lose your money. So those two things, those two things right there basically mean that miners, when they pick their transactions to package into a block, they pick them such that when they're actually evaluated, none of the runtime limits are exceeded in the process of evaluating that block. So that's the dynamic aspect. So whenever you evaluate a Stacks blockchain block, the system is keeping track of how much compute resources are actually used going forward. So, but miners don't necessarily know how much compute resources a transaction will actually take when it runs, but they do know the upper bound of what that could be. Here's an example. Suppose that I have a simple smart contract that says if the Bitcoin block height this gets mined in is even, then do something that costs 2,000 runtime. If it's odd, then do something that costs 1,000 runtime. We don't know whether or not the Bitcoin block height this block will get mined in is going to be even or odd. So what the miner does know is that no matter what happens, it's going to cost at most 2,000. So when the miner actually goes and produces a block that has this transaction, they might simply assume that this transaction costs 2,000 runtime, and when they're picking transactions, they just act accordingly, conservatively, to make sure they don't produce a block that's invalid. So then when the block actually gets mined and picked up, the transaction might evaluate to 2,000 or might evaluate to 1,000 runtime costs, but either way, the miner has produced a valid block. So that's that notion of static runtime assessment. You can look at the transaction and figure out the maximum it could cost and use that to inform your mining decisions. Like maybe you have different strategies here. Maybe you're a less conservative miner and you expect a higher transaction fee from a transaction that could be invalid or does take a very high maximum has a very high maximum runtime. Like you might charge the user for the worst case possible scenario. Like you might mine a transaction only if the user's transaction fee for it is high enough to cover the worst possible runtime execution, even if that doesn't actually come to pass. So that all these things that miners have to consider before they produce the block, that's the domain of the static cost analysis framework here. Because miners need to make sure they don't produce invalid blocks, but they also need to make sure that they are only picking up transactions that are going to be worth their while. Like, because they can't take a transaction fee due to out of gas error, so they have to make sure that users are paying for the worst possible runtime cost of their transaction in their transaction fees. All the while, though, the system is dynamically looking at the runtime use as the block gets evaluated to make sure that the block itself doesn't exceed the compute budget once it actually gets mined independent to the chain.
Awesome, thanks, Jude. Aaron, is your mic working, by the way?
Let's see. I think so. I'm highlighted green now, and stuff is happening when I speak. So.
Awesome. Yeah. I can hear you. Hopefully everybody else can. Maybe you can answer this next one. This is like a really basic one, but for those that didn't take like an algorithms and data structures class in a CS program at university or whatever, could you explain a little bit about like what these cost functions are and like how functions like this are used to kind of classify algorithms and in this case clarity functions and like how we use cost functions and like what does it actually mean when you look at one of these functions, because they're typically kind of just symbols and constants.
Yeah, sure. So so I guess at a basic level or the fundamental level, like a cost function is just like an arithmetic function that takes some inputs and then like produces like a number out. across these different dimensions of like read count, write count, the dimensions that Jude had mentioned earlier. But what these cost functions are trying to describe is like the amount of computation required to execute a given clarity function. And then the inputs to these functions are like some measure of the inputs to the actual function that you're trying to measure the cost of. So for example, if you're trying to measure the cost of a simple arithmetic operation like plus, the cost function is pretty simplistic because when you're adding two numbers together, adding two numbers is sort of always the same runtime cost. It's just evaluating sort of one operation on your CPU, whatever, but you have a constant time function. As things get a little bit more complex and you look at a clarity function like, say, a hashing function that takes a variable sized buffer as an input, the amount of work that your computer actually has to do to evaluate that hash function depends on the size of the input. So if you have like a 100 kilobyte buffer that you're trying to hash, your CPU is doing this thing where, it's sort of like combining all of these bytes down into a hash and rehashing. So there's like a linear growth component based on the input size. You would still have some constant component. But yeah, so you end up with these functions that tell you basically based on the input size, what is the expected runtime, what is the expected number of reads or writes being done to the backing store, all those kinds of things. And so for Clarity native functions, these cost functions generally look pretty simplistic. But if you're doing static analysis on like a user-defined function, you could end up with sort of more complex cost functions.
Thanks. You want to take this next one?
Yeah, sure. I think it could be useful to maybe talk through the cost functions of some of the functions in Clarity, or some of like the operations that happen in Clarity, and like how we kind of derive those costs. So yeah, Aaron, if you could talk to me the cost function of like a variable lookup and like what the function actually looks like.
Yeah, sure. I'm gonna pull up the like exact SIP specification for variable lookup just so that I have a standard way to talk about the variables going on in there. Yeah, so for a variable lookup in Clarity, basically like the Clarity VM is doing a couple of things when it's trying to resolve a variable. Like you could have a variable that's defined at the top level of your contract, like define constant defines a variable at the top level of your contract. Or you could have a sort of local binding for a variable. So if you're in a function, you could have a function argument that's locally bound. You could be nesting let statements, which means that you'll have these sort of sub contexts. And in these contexts, you're binding a variable sort of locally. And so the way that the Clarity VM resolves a variable or looks up a variable is it searches through these contexts. So if you're in like this nested let context, the Clarity VM actually has to look in your sort of most local context for the variable. If it doesn't find it, it looks in the next, like the parent context, and up and up and up. And so because of that, the actual cost of doing a variable lookup is linear in the context depth at which you're doing the variable lookup. So like if you're 7 let statements deep, you're going to have a different cost than if you were 4 let statements deep. So that's sort of the first variable in component of the variable lookup cost. The second variable component is actually the size of the variable that you're looking up, because Clarity has this particular cost model where every time you use a value, you can think of it as essentially copying the value. It's like copy semantics is what this is called. And so when you actually do the variable lookup, it sort of clones the looked up data into the current context, so it can be consumed by something else. So if you store it, you're not charged that copy or clone at a later date. This makes the cost model a little bit pessimistic, but more predictable, because you know exactly when you're going to pay for a copy. And so that's the other thing that goes into a variable lookup, is that you're paying for that copy up front.
What were the other like copy semantics that you guys like considered when designing Clarity? Aaron, if you can answer.
Yeah, sure. So I don't think we really seriously considered other copy semantics, because other copy semantics, you basically have 2 other options for your copy semantics. So one is you could say sort of explicitly everything is a reference unless you explicitly clone it. This would be pretty painful programming model in a functional programming language. Like you could imagine, you're sort of peppering your code with these clones all over the place. The other copy semantics would be sort of lazy copy semantics, where the Clarity VM sort of knows when it actually needs to do a copy, and it copies at that point. And then you could do dynamic cost assessment, where you only assess the clone when it's actually needed by the VM. The problem with that approach is that it would break static analysis of costs, because the static analysis system would never be able to figure out like how the lazy cloner is actually working, which was why we didn't go with that approach. Technically speaking, we probably still could have. It would just make the static analysis sort of less accurate, but it would only make it less accurate in sort of a strictly pessimistic way. So like the static analysis would sort of always be more pessimistic than the actual runtime cost assessment. So it would be possible, and we could like revisit this copy model in, say, like future versions of Clarity and future network upgrades, things like that.
Okay, cool. Yeah. Reed, do you want to get the next question?
Yeah, so I feel like at this point we've kind of had a good overview of like what cost functions are and how they're used in Clarity. A big part of this SIP is just like actually writing out different proposed cost functions for different Clarity functions and different like expressions in Clarity. I feel like for the sake of time, like I just don't think we can or should just go through those one by one. So I think maybe the next kind of interesting thing to talk about is like the section of the SIP that describes the memory model and memory limits. Maybe Jude, you could tell us a little bit about like how like memory usage limits are applied to contract execution, and like what kinds of operations in Clarity actually consume memory.
Sure. So they all consume memory after a fashion. Like, you got to represent the state of the VM somehow, and that costs bytes. So what the implementation does under the hood is, as you're evaluating the code itself, so as the interpreter is running through the source code, every time the interpreter takes an action, so you see a keyword of some kind, you see a function that has to be evaluated or applied, the act of evaluating is paired with basically incrementing one or more of 5 counters. Right, so you have the 5 different dimensions that are being measured. So each time you do something in Clarity, those counters get incremented based on what the cost function for that thing you're doing says you have to do. So not only are things like declaring variables or doing basic computations on them going to cost you something, but even things like evaluating an if statement or evaluating a function like map or fold, those things will cost some runtime as well. So as the transactions in the Stacks blockchain epoch are being evaluated, these counters are just continuously incrementing, depending on what each Clarity built-in's cost function says have to happen. So at the end, by the time you reach the end of the block, as you're running, each time we increment one of these counters, we check it to see whether or not it reaches the maximum budget. If so, then transaction processing aborts and the block's invalid, and the state of the VM is rolled back to the very beginning of the system epoch, and the block data is discarded. If it doesn't, if you reach the actual end of the transaction stream and you're still under budget, then great. The system continues processing the block, you get your Coinbase and your transaction fees, and all that is taken care of. Each time you check out one of these Clarity built-ins, the system will load up the cost function for it, and this cost function is, as Aaron mentioned, an arithmetic function, so it does no input or output. It can't load or store, or really even declare variables. It just computes a function of the instance characteristics of the thing being done. Like, suppose you're adding 2 numbers, your instance characteristics, your instance characteristic is the number of numbers being added. So, add 10 numbers, you get cost 5 times as much as adding 2 numbers, for example. And that's how that's how we figure out the right amount of resources to add to the cost counter as the transaction stream is being evaluated. Does that answer your question?
Yeah. I guess one follow-up to that is could you maybe explain how size of different types in Clarity plays into that? Given that types can contain sizes in the Clarity language.
Yeah. Okay, yeah, I see what you mean. So in Clarity, so obviously in general programming languages, different types will have different sizes. Like a string that's 100 characters long is 100 bytes. Or if you're using UTF-8, it might be as big as 400 bytes. An integer on a 64-bit machine is usually 8 bytes, because that's how many bytes are required to represent 64 bits. In Clarity, we have 128-bit integers, so 16 bytes per integer. We have this notion of a buffer type, which can be, between 0 bytes long, and I think 1 whole megabyte is the upper bound for that type. But unlike a lot of programming languages, in Clarity, if you have a type that has a variable size, the type itself represents the maximum size that the contained value is allowed to have. So you can't just have a buff for a buffer. You have to have a buff 10, which is a buffer that is at most 10 bytes, or a buff 100, which is a buffer that is at most 100 bytes. So if you look at Clarity code, the type signatures of the things that you load and store, if the contained value has a variable size in practice, you must specify the upper bound there. That gets used by the cost function. That gets used by the not the cost function itself, but by the static analysis pass to ensure that no matter what code paths gets taken, the miner can at least know the most costly it can be, and use that to determine whether or not a transaction has a sufficiently high fee when it's being considered. In practice, though, if you do something like add up the numbers. Or sorry, if you do something like instantiate a variable that's like a list of integers that's at most 100 units long, the memory you're actually billed for is the size of the list itself, not the maximum size it could be. So if I instantiate a list that has 3 integers in it, even though it's typed list uint 100, I'm still only being billed for 3 uints. Does that answer your question? Like, you have this type system that expresses the maximum possible size of all the things being stored in order to help miners do a static pass over the transactions. But when you actually run the transaction, you're billed for however big or small the contained data actually is when the code is executed.
Yeah, that makes sense. Thanks, Jude.
Now I think we can talk about, so earlier we kind of mentioned how we have a mechanism for voting for new cost functions for clarity functions. So I think we can kind of talk about what that process looks like. So first, can we talk about what the process for publishing a new cost assessment function is? Aaron, if you could answer that.
Yeah, so as I guess we've mentioned sort of briefly in passing a couple times, these cost functions that are being evaluated for each function to assess their costs, these are like simple arithmetic functions, but they're actually defined in Clarity. And so we have this like cost voting system that allows you to like update or network participants to vote on updates to these functions. But before they do so, they have to publish the candidate function. And so the process for publishing a candidate function is basically the same process as publishing a smart contract, except that the smart contract needs to pass an arithmetic only check. So when you publish the smart contract, it's run through this static analysis pass that determines whether or not the smart contract uses any functions that aren't arithmetic. So, you know, it's if the smart contract is doing like database reads, it's rejected, or it tries to like bind variables, do contract calls. Like there's all sorts of things that would make it illegal for arithmetic only. So if you publish a smart contract that passes that check, then that smart contract could validly be used in like a proposal for updating a cost function for one of the Clarity functions.
And is that check happening when you publish the contract or when the proposal is submitted?
In the implementation, it happens when you publish the contract. Ultimately, in terms of like sort of the consensus state of the network, it doesn't really matter when that check occurs. Like it could do it lazily, but I think in the implementation now, the check is pretty cheap and it's done just at the time of publishing the contract.
Just curious, is there any other use for the arithmetic only checker, or is it pretty much used for the cost assessment?
For now, it's only for now it's only used for the cost voting contract. I suppose in a future version, you know, the sort of arithmetic only status of a contract could be exposed to other smart contracts. Like it could be exposed to through the Clarity language, and then you could do something where, you know, let's say you have a contract and you want to accept trait objects, and like you only want to call into trait implementers that are arithmetic only, then maybe you could do a check that way or something. But for now, that's the only use.
Cool. Yeah, so just like moving on with the, you know, cost voting process. How does voting work in this process, like once you submit a proposal? Jude, if you can answer that.
Yeah, sure. So the first step would be to publish the contract that is an arithmetic contract. So no IO, just takes inputs of instance characteristics and outputs a numeric value. Once that smart contract exists as a potential cost function, what would happen is, and I don't have SIP-006 in front of me here, so this is just a high-level description. Feel free to look at the text itself to figure out the exact parameters. What happens at a high level is a fraction of the people who hold stacks, I believe it's like 30% or something like that, but again, double check SIP-006 for the actual number. They call into a cost voting contract in the stacks chain's boot code in order to provide the name of this contract that has the cost function and the name of the method that is the cost function, and vote with their stacks to say, I would like this other existing function, like a Clarity built-in, or even another function that's already widely used in Clarity. I would like this particular function here to have this cost function going forward. So if the threshold is met, like if enough people vote for the same function to have the same cost function, then the cost voting smart contract locks this in, considers this new cost function to be a replacement candidate for the old cost function, and then gives miners a chance to veto this. So if miners do not veto this, they have a period of time at which they can use the same smart contract to state that they do not approve of this new cost function. Then if they don't veto it, then the part of the code in the VM that looks up the cost functions and figures out, by how much the runtime cost of the whole epoch should increase each time you run this particular smart contract into consideration. The code that looks up that cost function will now look to this new voted in cost function instead of the old one going forward. So here's actually an interesting example. Right now, there is no Clarity implementation of an ED25519 signature verification. Suppose that someone writes a function that does this in Clarity, like they make a smart contract for ED25519 signatures. And suppose it gets wildly popular. Like suppose people really like this function. They want it to become so widely used that the system becomes congested repeatedly from people trying to call into this expensive Clarity implementation. So what the cost function system could do is the people who hold stacks can say, hey, we're all trying to use this signature verification scheme. Let's make this particular function cheaper. And someone publishes a cost function for it that is a lot cheaper than what's actually costing to run the Clarity code. They vote for this new cost function. The miners don't rebut it. So now going forward, you can call into this particular function a lot more per block because it's now billed a lot less than it would have been in the past. What you can do after that fact is you can release a version of the node software that implements a Rust implementation of that Clarity code so that the actual wall clock time of processing that block it becomes a lot smaller. Old nodes are still compatible. They'll still bill you the same amount. It's just because they're running the Clarity code instead of the Rust native implementation, it'll just take longer to evaluate blocks, but they'll still derive the same state, and the system won't undergo a net split or anything like that. But yeah, that's like an example of how and why you would execute this cost voting system.
Thanks, Jude. I can fill in a few of the details from the SIP there. So you mentioned there being a voter threshold. So the way that it currently works is that basically anybody can submit a new cost function just by publishing a contract, as you mentioned. Then you call into the cost voting contract, and there's a function for submitting a proposal. And you point it to the cost function that you previously published in a different contract. Then it returns a proposal identifier if the function works properly. And then you use that proposal ID to vote. So the threshold is that when you vote, you have to actually send stacks tokens to the voting contract, which ultimately will get returned to you, but it's just kind of like a staking mechanism, if you will, for committing your vote with your, with the stacks that you hold. Currently, the contract will only let you confirm a vote if a proposal has, I think, 20% of liquid stacks tokens. So it's pretty difficult to actually get one of these votes to pass. And I think was kind of part of the design of this system was we wanted it to be not necessarily the easiest thing to change these functions, but something that is possible if the network wants to do. And so once one of these proposals has been submitted, people can start voting on it. There's like a window within which you have to submit your votes. Otherwise, if the window expires and 20% hasn't passed, the proposal expires basically. There's also functionality for miners to veto a function. So if the miners for some reason don't like a cost function proposal, there's a separate function that allows them to kind of submit like a veto vote. And veto vote is not actually a threshold. It's actually just like a number of vetoes that's required. And I believe that number is currently set to 500, I think. Yeah, anyway.
It is 500. Yeah. Yeah. Wait, Reed, did you have a question? Or
Yeah, so I guess like Jude's response previously, there was kind of a lot to unpack there. I wanted to like dig deeper into what Jude was talking about with like this ability to kind of introduce new native functionality to the language that is enabled by the cost voting functionality. Could you maybe explain a little bit about like why can't we just if we didn't have this cost voting system, be kind of a pain in the ass to introduce a new native function, right? Like it would probably result in, or I think definitely result in the network hard forking. Could you explain why this system allows us to potentially introduce new native functions without a hard fork happening?
Sure. Before I do that, though, I should just want the audience to know Reed designed the cost voting system. If you look at the git blame, if it breaks, you know who to blame. That's Reed. We should be asking him the questions about the cost voting system. But it's great though. Like the cost voting system, I think, is one of the most interesting ways to de-risk this need to add new functions as the need for them surfaces over time. And I'm glad that we have this mechanism in the Stacks blockchain. I think maybe the closest real-world system to it that exists out there might be Tezos with their vote to upgrade the consensus rules. We're not quite as radical as that, but the system is powerful enough to make it so that it becomes possible to quote unquote add new native functions to the Clarity VM with the constraint that they have to be expressible as Clarity itself. So the example I used here is this notion of a new crypto signature verification. So we can't just add this as a new native Clarity built-in because that would mean that old nodes that don't have this new native function but would be unable to process blocks that contain calls to the new native function. So in order to, and of course if that ever arose, like the chain would split. Like old nodes would reject a block that had a call to it, new nodes would process it correctly, and they would forever stay disagreed. So what cost voting does offer us a way to do is if you can make it so that the new function you want to have in the Clarity runtime can be written in Clarity, then we can make that, then really the delta between adding a new native function in Clarity is really just a matter of actually making a Clarity implementation and then later on making a accelerated implementation that does the same exact thing but doesn't require the interpreter to get involved. The only real difference between adding a new contract call, making a new public function that has the new method, and this right here is just making sure that the function itself has an appropriate runtime cost. So verifying a cryptographic signature, for example, in Clarity would be very expensive. You would have to implement like this notion of, really big number multiplication, really big, like over a prime field, or a semi-prime field. In the case of Twisted Edwards, you would have to implement encoding and decoding scheme in Clarity for representing signatures as buffers, and stuff of this nature. Like, it would get really expensive to do this, like possibly even exceeding the block budget itself to do this. But as long as it's expressible within Clarity, then this cost voting system can be used to declare that this particular function, after a new cost function is voted in, would only cost so much. So all that really means is that we make it possible to, what that really means now is that like different versions of the Stacks node software can have different implementations of a particular publicly callable function. They can either be in the Clarity itself, as is in the smart contract, or it can be like in an accelerated Rust version that's implemented in Rust itself. It could even be something else entirely. It could be like a loadable module in a different language altogether. But the point is, as long as all of the nodes everywhere will execute the same state transitions, and that includes making sure that executing a particular function has the same cost and the same data gets loaded and stored into the marfed index. As long as all that remains true and you get the same state root at the end of processing a block, then everything's going to be fine. Like all the Stacks nodes, no matter how old or how new they are, will all process the same blocks the same way, and they'll all stay in sync with each other. The cost voting mechanism just means that you can add these new functions in a backwards compatible way, while still reaping the benefits of having a new native function being really fast and having an efficient implementation under the hood. As long as the cost function says that the function is cheap enough, is sufficiently cheap. Like if you have a new native implementation of a signature verification algorithm, it would be a lot cheaper in practice. Like running just the thing on your computer, it would take a lot fast. It would be a lot faster to run if it were native. Just making sure that is captured in the VM itself, so that no matter what version of the software you're running, you assess the same cost as the new native implementation. Then everything should be fine. That's kind of rambly.
No, thanks, Jude. That's awesome. I think we've more or less covered everything in the SIP. We have a bit of time left, so if anyone in the audience has any questions, please raise your hand.
Going once, twice.
I have
think we
another
might-
question.
Oh, good. Okay.
Okay.
Yeah, go for it.
Yeah, if people don't have other questions. So yeah, the way that cost voting contract is set up now, and I might be mistaken, so like let me know if I'm wrong. It seems like you basically are transferring your like actual STX over to the contract in order to vote. I'm wondering, like, in the future, like for example, like for exit at block height, which is like a proposal we're considering now, we want to allow stackers to vote too. So I don't know, in the future, like, would we consider trying to get like stackers to be able to vote in this cost voting function? I mean, contract as well.
So the nice thing about, oh, sorry, Aaron, I saw you unmuted there.
Oh yeah, I was just gonna say, I kind of like that idea, and yeah, I'd be supportive of like exploring some like the consequences of it. I mean, the risk is just that as you make it easier to update these cost functions, the changing cost functions can be kind of disruptive to the network. Especially, if miners are doing sort of more advanced static analysis at some point, they might have to recompute those things. So it can be disruptive. So making it easier on some level has trade-offs. But yeah, getting stackers more involved in network governance, I think, is in general a pretty good idea.
I know that one of the rationales for making it so that stackers could not vote on this is because it forces people who would otherwise be stacking to forego the opportunity cost in order to cast this vote here. Whether or not that rationale holds water now, I think maybe is a bit murkier to me, but that was at the time one reason we considered this, doing it this way. because again, like the trade-off here is like the easier it becomes to add new cost functions, the riskier it is to the network, because you can imagine like you get the cost function wrong, or you apply a cost function on a whim that turns out to have bugs in it, or maybe someone managed to make a malicious cost function that makes a very expensive operation very cheap, thereby opening a DDoS vector into the chain. So it's really a balancing act. Like you got to find out, like you got to make it so that cost functions can be done if there's actually a need for it, but they shouldn't be so easy to do that it makes it possible for people to just grief the system.
I would worry that allowing stackers to vote would almost make voting too compelling in a way. Like part of the trade-off of voting is that you don't have access to your stacks for a while and you can't really do anything with them. But I don't know. It's definitely interesting to think about. And
one of the other risks with cost voting in general is that, like, you could imagine, so that every blockchain community and every blockchain implementation has to grapple with this. There's no such thing as a blockchain that has too high of a transaction capacity. Like, there's always going to be people will always want transactions to go faster, and they will always want bigger blocks, because why not? It's free space. If you can have free space, people will use free space. What that means for cost voting is that people will always vote for cheaper cost functions if it means you can cram more transactions into a block. Because why not? Like, your transaction fees would go down, blocks could do more. The existential risk that poses to the network, however, is that if it becomes so intractably expensive to evaluate Bitcoin blocks, then no one will run nodes. Like, a lot of the really high TPS and high bandwidth blockchains out there, like Solana and EOS, require basically a small supercomputer to run nodes. And that kind of is problematic, I think, for us, because we're trying to build the user-owned internet, but to us that means you should be able to run a node on your consumer hardware. You shouldn't need to go out and rent or buy a multi-tens of thousands of dollar computer just to run a node. So making it too easy to vote for cost functions to make everything really cheap kind of runs counter to that end goal. Because what we really want is for people to be judicious about it in order to make sure that the chain is able to upgrade itself and add new features over time. But what we don't want is like people just trashing the chain for a temporary boost in transaction throughput that would leave the chain worse off in the long run.
Yeah. Okay. Yeah. That makes sense. I didn't consider that. I actually do have another question, but Shannon, do you have something you want to say?
No, all good. If the rest of you have time, go for it.
Okay, yeah. So my next question has to do with like minor incentives for vetoing. So it seems like minors would, to me it seems like they would always want to veto, just because like, okay, like if they if someone if basically the network is voting for a cost function that's cheaper, once static analysis happens, miners would have to recompute the static analysis for all those for all the contracts that use that function. And like two, that would like lower the runtime cost, which means that one, they might have to, add more compute, and like lower transaction fees. I don't know, like it just seems like it makes sense for miners to veto in most cases.
But miners also want like more people to want to use the network, right? And so like I think there's this, you kind of have to like find this middle ground between like wanting the fees to be expensive, so or not the fees, the costs to be expensive, such that the work that they're doing is perceived to be worth more, and actually kind of having costs that are agreeable, I think, for stacks holders, right? Because otherwise, if the costs are ridiculous, people aren't going to want to use the network.
Yeah, I think that there's kind of the miners' incentives, I think, can be fairly complex in this situation, because it's also if the cost of evaluation goes down for some functions, like maybe a new native function is introduced and there's efficient ways to compute it. If the cost goes down, it means that miners can include more transactions in a block. And in many cases, that means more profit for miners. Like it's not exactly the case that if block sizes go down and like suddenly transactions need to compete in like a fee market for one another, that miners would make more money in that scheme. It may make less because the demand for transactions is actually going down.
There's also precedent in Bitcoin, at least, for miners actively willing to upgrade the system to make it better. Like we just had Taproot, for example, on Bitcoin have the speedy activation go through. Like that's going to add more complex evaluation rules for Bitcoin blocks that will be borne by all miners, but yet miners still voted for it. Same went for SegWit, same went for check block time verify, even same went for pay to script hash. Like those were all after the fact upgrades that were ushered in through miner votes. So what that tells me is that there is evidence to suggest that Bitcoin miners, or at least miners in general, like Bitcoin miners specifically, but we also anticipate this will be true for Stacks miners, they will want the system to get better if it means that more people want to use it, because in the long run that means more money for them.
All right, cool. Thanks. That makes sense. Yeah, that's my last question.
Cool. Any other questions from anyone? Now's your chance. Raise your hand. Oh, we do have one. Hold on one second. I know we're a little bit over time, but we have one question. Looks like I now has joined. Hold on.
I think you might need to accept the invite to speak.
I did, yeah. I'm not sure why it's being slow to pull over.
Oh no, I'm talking to the
okay.
person, because like you invited him, and like I think they have to like accept it.
I know. Here's your chance. You can accept the invite. That would be great. I don't know. It's not moving over. Perhaps perhaps we can follow up in the stage chat if that's all right. Yeah, I don't know why it's not going. Sorry, everyone. I sent through an invite request too. Giving it just a couple more seconds. Huh. I invited him to speak too. Sorry about that. I wish it was working. Yeah, if you wouldn't mind posting the stage chat, that would be great. Just checking again. Nope, no good. Okay, cool. Well, thanks everyone. Thanks, Pavi, Aaron, and Jude. And Reed. Our next session is going to be on July 14th. We're going to cover SIP-7. I posted the link in the stage chat already. Thanks again for joining us. See ya.
Bye, everyone. Thanks for coming.
Thank you.